All right, so here's the nearpod video for our lesson on annual rates. All right, it says Sue put $4,000 into an account at Bank of America. She's amazed that she can earn 20% interest every year, right? Which is not realistic, but if you could, you should put all your money into that account. All right, and so how much does she have total after 5 years in this account? So what we want to do is create some variables here. So normally we do X and Y. All right, so in this case, we're going to use T for years, okay, time, years, right? And then this is money in the account, okay, the amount. So we'll call it A of T. Okay? And so when time is 0, okay, so no time has passed, so the initial amount in the account is 4,000. And then when we plug in 1, okay, what are we going to get? So, well, we don't have a function to plug it into yet. So what if she earns 20%, right? She has 4,000. She earns 20%, right, which is 0.2 or 1/5, right? So if you multiply 4,000 times 0.2, right, what are you going to end up with? All right, so you're going to end up with 800. So she earned $800. Okay, so what does she have in her account? She has the original 4,000 plus the 8,000, right? And so she's going to have 4,800 in the account. Okay, and so we could do that for 2. Now we're going to take, okay, the previous amount, the 4,800 now. Now she's going to earn 20% on that amount. All right, and so how much money is she going to have in the account now? Well, she's going to earn 960 bucks. So we add 4,800 plus 960. All right, and we get 5,760. All right, so we could keep doing that and keep doing that until, I mean, this one only wants for 4 years, right? Or 5 years. So we'd have to do it 3 more times. Is there a way to create a function that models this growth? All right, and there is. So we're going to look at that. What should the equation of A of T be? All right, and so we know our initial investment is 4,000. That's going to grow for 5 years. What's it growing by? So every year, look what I'm doing. I'm multiplying by 0.2, I'm adding 800. I'm multiplying by 0.2, and I'm adding that amount, right? So that adding is always that initial amount. So what I'm doing is technically 120% of the previous amount is what your new amount is. So I'm doing 1 plus R, okay? And in this case, R is 20%. So we want to write that as a decimal. And then how many times am I going to do that? Well, once, twice, 3 times, 4 times, 5 times. So I could write 1.25 times, or I could just raise that to the 5th power. All right. And so, well, the equation, would be T, right? And then we want A of 5. So we're going to plug it in to this equation, 4,000 times 1.2 to the 5th. And where'd the 1.2 come from? I just added 1 plus 0.2. Right? It kind of stands for 120%. It's 120% of the previous amount. But we're doing that 5 times because we want the 5th year. All right, so what is that going to equal? Okay, so after typing that into the calculator, I got 9,953.28. It's a lot of money. right? So more than doubled already in 5 years. Pretty incredible how compound interest works like that. All right, but again, 20% is unrealistic. Yeah, if you put into a typical savings account, um, you're not going to even get a percent at a bank like Bank of America. They have money markets. Okay, they have CDs where you might be able to get a little bit higher percent, but you get that higher percent, you've got to kind of forfeit the rights to your money a little bit. All right. So the question was how much she earned, what would I do? I would just subtract 4,000 from that. Right. So she earned $5,953.28 in interest. All right, let's look at this one here. So Sue took out a loan from her dad for $4,000, okay, for a Honda Civic with 100,000 miles on it. She has agreed to pay 20% of the total owed every year back to her father. Okay, so we want to know how much she still owes after 6 years. All right, so our output is the amount still owed. That's like the balance left on the loan. All right, so she's gonna pay back 20% every year. All right, this is not how most loans are structured, but for this case, we will follow this. Use the monthly payments and you pay back principal and interest at a fixed rate. Okay, but let's go ahead and again, we're going to do T for the number of years. All right, and the A of T here is the amount still owed. All right, it's the output. So, right after 0 years, she still owes the $4,000. Right after 1 year, how much does she owe? So how much did she pay back? She paid back 20% of that. All right. So again, 4,000 times 20%, we know we just did it, was 800. So if she paid back that, now I'm subtracting 4,000 minus 800, okay, which equals 3,200. All right. Again, this is not how most loans are structured, right? There's no interest gained on it. There's no interest on this loan. Her dad is doing her a favor, right? She's just paying back 20% a year. All right. So now after 1 year, she owes 3,200. So the next year, how much is she going to pay back? Okay. So now it's 20% of 3,200 because she's only paying back 20% of what she owes. Okay. So the total owed every year. So again, I multiply that by 0.2, and now I get 640. And so if I subtract 640, so 3,200 minus 640, this means 2,560. And so on. So we want to do this, okay, until we get to year 6, okay, after year 6. So we're going to pay back year 6. How much is owed? Again, so we want to do, what is A of 6? Well, very similar to the other one, right? You have that principal amount, but this time you're subtracting that 20% off, right? So my formula, my A of T formula, okay, is going to be my principal amount, which in this case is 4,000, right? And every year we pay 20% off, okay? And so what we're actually paying, what's left, because remember this represents what's left is 80%. If we pay 20, what's left is 80%. So that's 1 minus R in this case. And we know that R is 20%. We'll plug that in here in a second, raised to the T. So for our formula, okay, we want A of 6. What are we going to plug in, right? We have 4,000 times 0.8 raised to the 6th. All right, and that's how much she's going to owe. I'll pause it, do that on my calculator, and come back in a second. All right, so I get, on my calculator, I get A of 6 is going to equal $1,048.57. And so that's how much she still owes her dad after 6 years. So every year, right, she's paying back less and less because the amount owed is less. So 20% on less is less. So she structured it and where she's paying most of the loan back early on, okay, and then a little bit left. But now using this strategy, will she ever pay off her debt? And the answer is technically no, right? Because she's always leaving 80%, right? She's only paying 20%. So every time she makes a payment, she's leaving 80% there. Now eventually it'll get so small, okay, that she'd probably just pay it off. But this goes back to the graphs we were looking at earlier, right? There's that asymptote. It never actually reaches zero, right? Those decay functions get close to zero, but never actually reach it. So there's that example. All right, so here's the formula. So this is for your notes, okay? So this is what we just talked about, okay? And so it depends if it's growth or decay. So that first example was an example of growth. The money was growing, right? And then the second one, the amount still owed was decaying. So the generic formula is the final amount, so A of t, right, where t represents the number of payments or number of years, your time period, okay, equals A, the initial amount, okay, so how much you either deposited or what you owe, right, and then it's 1 plus r for growth, 1 minus r for decay, right, and that's your rate of increase, right, so whatever percent they give you, and you're adding that to 1, right, put it together, and that's your growth factor. Okay, or decay factor, right? If it's 1 plus r, that's your growth factor. All right, so like in the first example, 1.2 was the growth factor, but 20% was the rate of increase. And then in the second example, 0.8 was the decay factor, and 20% was the rate of decrease. And as I said earlier, t is the number of time periods. Okay, so in the formula, the base of the exponential expression 1 plus r, that it will be an exponential growth function, right? Because it's going to be bigger than 1. It's going to make your growth factor bigger than 1, so it's growth. And then 1 minus r is going to make it less than 1, and in between 0, so that will be decay. All right, so Claire invests 5,000 in an account that pays 6.25% interest, okay, compounds annually. How much will she have after 4 years? So we don't need to do a table of values. We want to know A of 4. Let me make that a little bit skinnier. All right, so what is A of 4? Well, we know our principal amount, okay, so she invests 5,000, so that's what we're starting with. Okay, it's earning 6.25%. Okay, so we're going to add that rate to 1, right? It's 1 plus r. And so when we do this, okay, what is 6.25% as a decimal? Okay, it's real important that you do this right. It is 0.0625. Right? It's not 0.625. 0.625 would be 62%. Okay, 6%, right? Raised to the fourth power. All right, so you do your work. Okay, so you're going to get 5,000 times 1.0625 raised to the fourth power. All right, and so let me pause that, type that into a calculator. All right, and my calculator gives me $6,372.15. Remember, it's money, so you always round to the hundredth spot. And so that's pretty good return right there, right? Just in 4 years of earning interest, okay, or she gained $1,372 in interest earned in just 4 years. That money's growing, right? That's the power of compounding interest, right? The better the rate you can get, all right, the faster it's going to grow. Right? Where do you find the best rates? Not banks, right? You gotta take a little bit of risk and put some stuff in some stock market. That's where you're going to find the best returns. That's also risky. You may lose your money. All right, if you want security, right, you look for some bonds, okay, just regular money market accounts. Okay, those are some security stuff. All right, so this also works for anything, not just money, right? So populations grow, bacteria grows, some things decay, right? And they're all growing at exponential rates or decaying at exponential rates. All right, so it says this one says in January of 2011, the Australian humpback whale population was 350 and increased at a rate of 14% each year since then. Write a function to model population growth. How many whales will there be this year? All right, so let's write an equation to model this. So our population, okay, so the amount of whales after T years is going to be what we start with, so 350. It's growing by 14%, so 1 plus 14%, 1 plus 0.14 raised to the T years. All right, so what is our T? So this year, so 2021, so 10 years later. Okay, so it's growing for 10 years. This is what I need to figure out. 350 times 1.14 raised to the 10th. And again, I haven't mentioned yet, but obviously we're following order of operations here, you guys, right? We do exponents first and then multiply by 350. All right, so let's pause and type that into our calculator. So if I type that in my calculator, I'm going to get 1,297.53. Right, but we're talking about whales, so let's use a little common sense. Can we have a half a whale? All right, so we'd say the population, okay, it would be 1,297. We're not going to round up; it's a person. So how many whales do we have? We have this many whales. The 1,298th one is on its way. It's not quite there yet. All right, so there we go. That's our answer. All right, city population, which has a total was initially at 15,500, has been dropping 3% a year. Write an exponential function and graph the function. What is the population after 6 years? All right, so this one we want to graph it as well. Okay, so that's first set up the function. So what function are we even graphing? And so the amount of people, okay, in the city would be 15,500 times 1 minus 0.03 raised to the 6, well, raised to t. We're doing the function first. Right? When we answer the question, we'll plug in 6. Okay, simplify that again. Why did we do minus? Because it's decreasing. So this is a decay function. So 15,500 times 0.97 to the t. That's the function that we're graphing. All right, so if I had to graph this, okay, I know I only really care about the first quadrant, all right, because it starts right at year 0. At year 0, it's 15,500. That's where I'm starting, right? And then it's decreasing every year. Never going to go below 0. All right, so that's what we just have a little sketch there, right? To be exact, well, let's find out what A of 6 is. So again, we're going to need our calculator. Let me pause and type that into my calculator. All right, so when I plug that in, 15,500 times 0.97 raised to the 6th, I got 12,494.6. Again, these are people, so just go down to the next whole number there. All right. So on my function here, so if this was 6, right, wherever it hit the graph, that point would be 12,494. Right? And so again, this is a decay function. All right, it says a motor scooter was purchased for $1,000, depreciates at an annual rate of 15%. Write an exponential function to determine how much it's worth after 8 years. All right, so just go ahead and plug everything in here. So we're going to get A of t equals the initial price of the value of our scooter, right? It's going to go down 15% every year, raised for t years, and we want to know what A of 8 is. Okay, after 8 years, what is the value of our motor scooter? All right, so 1,000 times 0.85 raised to the 8th. So let's type that in to our calculator and see what we get. Okay, and I get $272.50, 49 cents. Went down a lot. Not a good investment there. All right, and then you guys have a little quiz at the end. There you go.